Question 1. So this is a quadratic curve. We've got the x squared, so this is going to be a positive parabola. It's going to be a smiley face shape. So we really want to start looking out for the symmetry with these y values. So let's kick off by working out when x equals 3. I'd always start off with the positives or the 0 and leave the minuses to last. So when x is 3, so substituting that into the curve, we've got 3 squared, which is 9, take away 2 lots of 3, which is 6, take away 1, which is 2. So we've got the coordinate 3, 2. Now, you can see that we've now got a 2 here, a minus 1 here, a minus 2 here. So now let's go and work out when x is 0. So substituting 0 in, we get 0, take away 0, take away 1, which is minus 1. Now at this point we've actually got some symmetry here. We've got a couple of repeated y values. So think of a pebble just dropping into a lake there at that point there, and then the ripples coming out. So that minus 1 ripples out to that minus 1, and this 2 will ripple over to this value here. So this is 2. We can just do that by symmetry. But if you want to check the value, substituting minus 1 into the curve, minus 1 squared is plus 1, minus 2 times minus 1 is plus 2, and take away 1 we get 2. So those are those values. For part B we plot a gentle curve. Now for part C, find the estimates of the solutions of the equation when it equals 0. Well, that's where the curve crosses the x-axis, so I think approximately that's at 2.4 minus 0.5. There would be some leeway in the mark scheme, so as long as your values are around there, you get the marks. Question 2. So we can see the patterns going from one column of grey squares to 2 columns to 3 columns to 4 columns of grey squares with the white squares on the outside. Now part B, work out the total number of squares needed to make pattern 7. So what I've done, I've converted the pattern to total number of squares. So we've got 4 squares here, 6 squares here, 8 squares here, and so on. So we can see that we're going up in 2s. So pattern number 7, so pattern 4, 5, 6, 7, going up in 2s. Just by filling in the pattern, we can see that on pattern number 7 we'd have 16 squares. Now if you want to work that out by way of the nth term, you can. We're going up in 2s, so that's 2n, and the 0th term would be plus 2. So when we substitute 7 in for pattern number 7, we get 2 lots of 7 plus 2 equals 16. Now for part C, AXA says the total number of squares needed to make pattern number 20 is double the total number of squares needed to make pattern number 10. Is she correct? Well, let's just work out how many squares we have in pattern 10 and 20. So pattern 10, n equals 10. Substituting 10 in, we get 22 squares in the pattern. Substituting in 20 for pattern number 20, we get 42 squares. And we can see that she's not right because obviously 42 is not double 22. Question number 3. So we can see with this pattern here we're just doubling the previous number to get the next number. So write down the 6th term of the pattern, 1, 2, 3, 4, 5, 6. So we need the next term, so we're going to double 16, which is 32. Now Jack uses a different rules. He says the first 6 terms of the pattern are this. Write down the 7th and 8th terms in his pattern. So again, I can see that we're just going up by 1, then by 2, then by 3, then by 4, then by 5. So to continue this pattern, the next step we're going to go up by 6. So 16 plus 6 is 22. Then we're going to go up by 7. 22 plus 7 is 29. Question 4. Well, I can see with my sequence that I'm starting off with 18, then I'm adding 6 each time, so I'm getting 18, 24, 30 and so on. I can see that my pattern is going to comprise even numbers. Now 603 is an odd number, so it's not going to be in the sequence because the sequence is just even numbers. Now for part B, no terms of the sequence of multiples of 7. Well, let's have a look. So just carrying on the sequence a bit, 18, 24, 30, 36, 42. Well, 42 is a multiple of 7, so that's just one example to show that the person is wrong. Question 5. So, just to complete the pattern, well, we need to have another triangle and a couple more circles. So that's what the pattern's going to look like. Now find the number of circles in pattern number 7. So let's go back and see how many circles we get, just to numerically understand the pattern. So pattern number 1 we have 3 circles, pattern number 2 we have 5, pattern number 3 we have 7, and so on. So we can see we're going up in 2s. So pattern number 4, 5, 6, 7, going up in 2s, I'm going to have 15 circles. Now Jane says pattern number 17 has 36 circles. Why must she be wrong? Well, similar to the previous question, we can see that our pattern comprises an odd number of circles, so 36 circles is not possible because 36 is even. Question number 6. So here's the next pattern. We're going to have 1, 2, 3, 4 rows and then the extra one on the end. So that's what our pattern's going to look like. So how many grey tiles are needed for pattern number 10? So let's just try and numerically understand the pattern for grey tiles. So pattern number 1 we've got 4 grey tiles, pattern number 2 we've got 7 grey tiles, pattern number 3 we've got 10 grey tiles, and so on. So we can see we're going up in 3s. So our nth term expression is going to start off with 3n because we're going up in 3s, but our 0th term, the term in front of the real first term, would be a +1. So our nth term expression is 3n plus 1. Pattern number 10 is when n equals 10. So substituting 10 into our nth term expression, we get 3 lots of 10, add 1, which is 31. Now, Jenny says, I will need exactly 46 grey tiles for pattern number 18. So let's see if she's right. So pattern number 18 is when n equals 18. So popping 18 into our nth term expression, we get 3 lots of 18 plus 1, which is 55. So she'd need 55 tiles. So Jenny is wrong. Pattern 18 has 55 grey tiles, not 46. Question number 7. So find an nth term expression for the number of counters in pattern number n. So pattern number 1's got 4 counters, pattern number 2's got 7, pattern number 3's got 10. So we can see we're going up in 3s. So 3n, and our 0th term would be +1 because that's 3 back from 4. So 3n plus 1 is our nth term expression. Now Bayo has 90 counters. Can Bayo make a pattern in this sequence using all 90? Well, if they can, when we go and solve the nth term expression equaling 90, then n will be a whole number because that would be the pattern number. So 3n plus 1 equaling 90. Can we solve that to get a whole value for n? So take away 1 from both sides, divide by 3, we get n being 29 2/3. So n is not a whole number, so 90 is not in the sequence. Question number 15. So the next term in the sequence is clearly 19 because we're just adding on 4. How did you get your answer? Well, we just added 4 to the previous term. Now, work out the 11th term in the sequence. Well, we could just go and literally keep on adding 4 until we get to the 11th term, or doing it by way of the nth term expression. We're going up in 4s, so that's 4n. Our 0th term, well, that's going 4 back from 3, giving us -1. So our nth term expression is 4n minus 1. The 11th term is when n equals 11. So 4 lots of 11 is 44. Take away 1, we get the 43. So is 79 a term in this sequence? Well, if it is, when we solve 4n minus 1 equaling 79, we will get a whole value for n. So let's have a look. We add 1 to both sides, 4n equals 80. Divide by 4, we get 20. So yes, 79 is a term in the sequence. It's the 20th term in the sequence. Question 9. So this question's all about the Fibonacci sequence. So just to remind you, and it says it here, to work out the next term in the Fibonacci sequence, you add the 2 previous terms. So for example, how did we get this 5? Well, we added 3 plus 2. How did we get the 8? Well, we added 3 plus 5. So the next 2 terms in the sequence, so first of all, 5 add 8 gives us 13. That 8 add 13 gives us 21. And then 13 add 21 will give us 34. So the 9th term in the sequence, 1, 2, 3, 4, 5, 6, 7, 8, 9, is 34. Now, show that the 6th term of this sequence is 3a plus 5b. So we start off with the 3 that they gave us, a, b, and a plus b. So the next term is going to be adding the 2 previous terms, which is going to be b plus a plus b, which is a plus 2b. Then the next term is going to be the previous 2 terms, which is a plus b plus a plus 2b, which gives us 2a plus 3b. And then finally, the 6th term, so the previous 2 terms, is going to be a plus 2b plus 2a plus 3b, giving us our 3a plus 5b, which is what we had to show. Now, given that the 3rd term is 7 and the 6th term is 29, find the values of a and b. So, 3rd term is 7. Now, the 3rd term is 1, 2, 3, is a plus b. So we know a plus b equals 7. Then we're told the 6th term is 29. Well, the 6th term, as we can see from b, is 3a plus 5b. So 3a plus 5b equals 29. So this gives us a little simultaneous equation to solve. So to line up our a's, let's choose to multiply equation 1 by 3. So 3a plus 3b equals 21. So taking away equation 2 from equation 1 once we've multiplied it by 3, which I've done up here, we get 2b equaling 8, so b is 4. And then b is 4, substituting that back into equation 1, when b is 4, a is 3. Question 10. So part A, draw pattern number 4. Well, pattern number 4 is going to look like this. So we're going to have 1, 2, 3, 4, 5 grey bars, and then the 4 white bits in between. Now, part B, how many grey rectangles are there in pattern number 8? So let's just go back and have a look how many grey rectangles we have. So pattern number 1, we've got the 2 grey ones. Pattern number 2, we've got the 3. Pattern number 3, we've got the 4, and so on. So we can see that the number of grey rectangles is always 1 more than the pattern number. So pattern number 8 is going to have 9 tiles. Now, Sue says there is a pattern in the sequence with exactly 50 white squares. Is Sue right? You must give a reason for your answer. So let's have a look at the white square pattern. Well, we have 2 white squares, then 4, then 6, then 8, and so on. So we can see that the pattern is just comprising all the even numbers. So yes, 50 will be in that sequence, so Sue is correct. Now, part D, a pattern in the sequence has exactly 20 grey rectangles. How many white squares does the pattern have? So, if it's got 20 grey rectangles, then we know that it must be pattern number 19, because we've said the pattern number is 1 less than the number of grey tiles. So pattern number 19. Now how do we work out the white tiles? Well, we multiply the pattern number by 2. So 19 times 2 equals 38. So just to go over that again, we first took away 1 from the grey rectangles, so we know it's the 19th pattern, and then because every pattern's got twice as many white tiles, we doubled the 19 to get 38. Question number 11. So expand and simplify. So expand is get rid of the brackets, and simplify is gather like terms. So popping in our clause, we have 2x times 3x, which is 6x squared, 2x times minus 2, which is minus 4x, 1 times 3x, which is plus 3x, and 1 times minus 2, which is minus 2. So that's expanded. And then to simplify, we gather the like terms. We gather the x's in the middle. Minus 4x plus 3x is minus x. So we get 6x squared minus x minus 2. Now for part B, to factorise a quadratic, well, we know it's going to be a pair of brackets with x as the first component of each bracket, because x times x gives us the x squared. Now these two magic numbers multiply together to be the term on the end. So our magic numbers multiply to be the 9, plus 9, but add to be the coefficient of x, so they add to be the 6. So which two numbers multiply to make 9 but add to be 6? Well, that's 3 and 3. Because 3 times 3 is 9, and 3 add 3 is 6. So our magic numbers in 3 and 3. So our factorised answer is x plus 3 in the first bracket and x plus 3 in the second bracket. Question 12. So similar to the previous one, a pair of brackets with x being the first term. And then we're multiplying to make the minus 15. But adding to be the minus 2. So these two magic numbers are 3 and minus 5. Because 3 times minus 5 is minus 15, but 3 take away 5 is minus 2. So we've now factorised our left-hand side. Our left-hand side is x plus 3, x minus 5. So our solutions are which x values make, first of all, this bracket 0, then secondly, this bracket 0. So x being minus 3 would make this first bracket 0, because 0 times whatever is 0. And then secondly, what makes the second bracket 0? That's x being plus 5. So you'll see that our two solutions are our magic numbers, but with a change of sign. Question 13. Now these are very difficult when we've got a number in front of the x squared, so don't be overly worried if you can't do these yet in third form. So how do we do these? Well, we kick off by changing the problem from being a 3-term problem to a 1, 2, 3, 4-term problem. Now how do we do that? Well, we're going to split this x term down 2 ways, and this really is going back to what we normally do. We need to go and find some magic numbers. Now what we're saying is our two magic numbers multiply, not so much to be the minus 15, but to be the 6 times the minus 15. So our magic numbers are 6 times minus 15, which is minus 90, but at the same time, as per normal, add to be the number in front of the x, which is effectively a minus 1 on this occasion. So which two numbers multiply to be minus 90 yet add to be minus 1? That is 9 and minus 10. Now that doesn't take us to the final solution, that just allows us to split this middle term 2 ways. So it doesn't matter whether we go plus 9x minus 10x or minus 10x plus 9x, we'll get the same final answer. I've chosen to go plus 9x minus 10x. Now once you've done this, we've got 4 terms here. So we start off by fully factorising the first 2 terms, and that gives us 3x open bracket 2x plus 3. And then we move on and fully factorise terms 3 and 4. And you'll see that if you do this carefully, just being careful with the sign here, we can get a repeated bracket. Now, next step is to turn this into a pair of brackets, which comprises the 2 elements which are presently not in a bracket. So that's the 3x and the minus 5. So that's where that brackets come from. And then our second bracket is the repeated bracket. Now, to get our solutions from this, because we've now factorised, we have to go and decide what value of x would make this first bracket 0. So we've got a little mini equation to solve. 3x minus 5 equaling 0. So add 5 to both sides and divide by 3, we get x being 5 over 3. And then secondly, what value of x makes the second bracket 0? So another mini equation to solve, 2x plus 3 equaling 0. We'll take away 3, divide by 2. Our second solution is x being minus 3 over 2.